500 degrees C. Yes, Professor Johnson?
On the same topic, if you're cooling the piston, would that hurt the performance of the reactor, since now you're kind of cooling things down, you're trying to keep things up at the same time, so is that cooling the reactor?
Yeah, so his question was, since we're cooling the piston with the fan, is that going to cool the reactor to the point that it doesn't work any longer? I didn't do any simulations on how much it would cool the outer shell. I don't think it'll have a big impact because there's about 6 inches of high temperature insulation between the cavity and the outer shell. So I would not think that the cooling of the outer shell is really going to affect the cavity at all.
But that wasn't shown in the image, right?
Yeah, that was not shown in the image, yes.
The question I had, though, the other question I had was about the motor and how you incorporated the square wave to agitate it a little bit. Is there anything like that? I'm concerned about the impact that might cause on other parts of the system. Is that a concern? Is it something you can resolve so that's not going to damage anything?
Yeah, so his question was about the square wave that's implemented. And we have tested it, and it seems to be fine. We haven't done any long-term testing. And our customer has expressed that same concern a little bit. And there's still the option in the system to just run a normal rotation, which was shown in the impact testing video.
And also along with that, this is kind of like a secondary, the square wave kind of came out of our one ASA for the like how to prevent buildup of cobalt oxide. So we got the square wave and the impact hammer system. So we kind of did them both as a way to tackle it, but the impact hammer, from the way it appears, we haven't tested on sun yet, it seems to be working extremely well. So just in talking with our customer as well, they anticipate just using the piston, and they can always switch it back to the sine wave if need be or things like that. So, yeah.
The part where the impact hammer strikes that cavity, the system stops for like half a second or a second. Was that a design thing that you guys implemented to the entire system? And if so, how much of a difference is that time for the entire cycle?
So, I'm sorry, can you repeat the first part?
Yeah. So where the impact piston strikes that cylinder, where the buildup is, it pauses there for half a second to let you hammer hit. Was that designed by you? Was that stop designed by you guys, or was that already implemented into the system before you got there?
Yeah, so the question was the pause when the piston hits the rotating cylinder, like, intentional?
Yeah.
Yeah, it definitely was. We wanted to prevent any damage both to the piston and to the rotating cylinder itself. So basically, it was just programmed in the system. Whenever it extended, it would pause, or at least slow down to the point where it wasn't damaging to the reactor itself.
Does that pause, does that affect the entire cycle at all, drastically?
I mean, it definitely does stop it, which isn't planned, but overall, it doesn't need to be a perfect cycle. Really, the effect we're going for is knocking the cobalt oxide off the walls, and the effect that it's stopping really is actually jolting itself. So, yeah.
Thank you.
Thank you.
Where's the other microphone? There's one up here.
Pocket. In like a pants pocket. You fool.
You fool. I'm just gonna clip it right here. I'll probably just hold it honestly.
It's live streaming and we're recording everything. We were like,
No one told us that. You know what? I was not made aware.
I just told one of his teams. I was like, yeah. I'm gonna call up my family right now, 10 minutes before, and be like, yo, it's live.
Hey, I know you're at work.
That's a great way of letting us know.
Yeah, I wouldn't.
No.
Hey, my mom's a nurse. Like, hey, could you just stop that for a little bit and watch my presentation? It's 20 minutes. Could you spare 20 minutes?
The first
Oh, you know what we should do is put the live stream up on the presentation and then have it live stream over and over forever.
Just like the drill bits, just like the bit sort one. This presentation never stops.
Never stops disappointing.
That's correct.
Yeah. That's
Good. Other than that,
Apparently took the
the more you know.
Yeah, we are already going to be kind of cutting it close with time, and now we have to figure out who's getting what microphone when.
If we get over, then we'll just be like, don't fuss.
thought about it, we were like, we go really
I should like our final presentation right into the microphone. Be awful.
Drill bits. Enjoy your summer.
Bam! School's out, kids. Hack us. Yep, that was what I was saying. Like, someone grab a microphone. So we're going.
Who just called the thing final oral report? Is that you guys?
That's us.
Nice.
Yeah, you should bit sort that or something. Delete it, please.
Bam.
What? Oh, I thought it.
Oh, this says bit sort, man. You're good.
BS.
Make sure it's all good.
What? Oh, I thought it.
Oh, this says bit sort, man.
Oh, okay.
Oh, it's going. Wait, the live stream's happening right now? Why did no one That's all good.
Infinite loop.
The live stream's happening right now.
That's terrible. Get it over here.
No.
What's up?
When do you think is the next time?
Dude, I don't know.
Okay.
So I know FMV. I know Friday and Saturday. Concert.
There's a chat? Yeah. Come in and see all my snide comments. It's right where's the mic? Non-school friendly. Well, we're gonna have to switch. That's what Eric said we had to do. How do you get it to do?
Oh, like last night?
No. That one. But is it going to be? I think it'll be okay. At least this one, yeah, I'll bet you Eric.
Oh, what?
If we do presenter view, it like comes all. It shows it up there too.
That's all right. I'm not worried about it. We'll be okay. I can get a timer on my phone like here.
Yeah, I was gonna put mine up.
Okay, then you should do that.
I already silenced my phone, put it in airplane mode.
About ready?
About ready.
Okay.
Okay, good morning, everybody. We have 4 presentations today. They're a little bit longer, so what we're going to do is kind of keep 2 or 3 questions after each presentation, because if we go too long there, we're going to multiply that by 4, and pretty soon we're out here too late. So we'll get 2 or 3 questions for each Q&A. The second thing is that I'm going to be sending around a sheet. What we're trying to do is monitor how people are doing with their jobs, but also throughout the semester we've been finding where you're at in the job search, and now we want to know where you're going. This will help us for future semesters so that we can assist people in their career choices. So I'm going to send this out, just kind of circulate it in a serpentine pattern there, and then we have a video and microphone set up here today. I was going to let Eric talk a little bit about the technology with the 2 different mics and how you'll handle that.
All right, so when you're presenting, there are 2 wireless microphones. Clip it on about chest level, so maybe 6 to 8 inches below your mouth. And you can just hold the transmitter, or if you have a pocket, you can pocket it. There's also a belt clip. The first person and the second person who are presenting will be mic'd up. When the first person finishes, they'll pass the mic to the third person, and then the second person will pass to the fourth, etc. So when you're doing the mic change, you're not interrupting your presentation. During Q&A, if you just stand near someone with a microphone, it'll pick you up well enough. So, any questions about how the mic passing will work?
So one thing I noticed in the first section, you gotta think of, if you're the speaker, you gotta be thinking about who you're gonna hand the mic to. So you'll probably be moving a little bit with the screen and so forth. Just make sure to end on the side next to the person that you're gonna hand the mic to, because sometimes people would end up on the wrong side. They have to scoot over, they try to do a Hail Mary with the microphone.
Please don't throw the microphone.
So in any case, yeah, it's just be thinking about who you're gonna hand the microphone to and end up on that side of the screen.
Great.
All right, are we about ready? Excuse me. Okay, ready to go?
Nathan, can you hold this?
I think the speaker is going to go over there, and
I'm inept.
here, and everyone else will go over there.
Is this thing on? I'm inept. Okay, Matt, when you're ready to go, just. It's bad luck. Bad luck to lose a button. Nathan, you hit that. Okay, if you don't want to stand by me, Nathan, you don't have to.
Okay, good start. I think we're ready.
We're ready.
Oh, at least one of us is. Good morning, everybody. My name is Matthew Nelson. I will be presenting with my team on the BitSort 1. Our advisor is Professor Jeff Will. So a little bit of an outline of our presentation today. We're going to talk about our project objective for this semester, or for these past 2 semesters. We're going to do a little bit of a system overview of what our machine actually does. We're going to go over the final design that we came up with for the mechanical, electrical, and computer subcomponents. We're going to talk about the prototype testing that we did, talk about some of the proposed improvements that we might have for this project if we were to do it again, talk about the lessons learned throughout this time that we spent working on it, and then go over a summary and do some questions. So our objective for this project was that we wanted to create a drill bit sorting device, which we called the BitSort 1. It was designed so that a user could automatically sort and size drill bits just by inserting them into the machine. It was designed to help prevent wasted time, as well as to promote a clean and more manageable work environment.
Okay, so I'll talk about the system overview here. So if we just follow the path that a drill bit takes, you load the bit into the system through this chute here, and then it falls through the chute onto the tray, which you can see marked up there. It takes the image at that point and then analyzes it. So it'll take a picture and do some computer vision algorithms and sizing metrics just to see what the diameter on the drill bit is. So after that happens, we actuate the motors using our Raspberry Pi, which is mounted up here, not shown. Then we send the tray over to the appropriate bin, so it translates this way, and then it'll tip in and out of the page to either excuse me, a bin in front or behind that tray. So it'll tip it, and then it returns to the home position to accept another drill bit. Oh, so just some final design components. This is our housing here. So the first part of it is the wood drawer shell. So that was designed, it's designated space on the left and the right side for our motors and other mechanical components, just so it can be separated from the drawer space, which is in the middle here. So the next part of that is our drawer, which is made out of sheet metal and wood. So you can see the sides are made out of sheet metal, and that's where those drawer slides are attached to. And then the front, the back, and the handle are all manufactured out of wood. And so it's stepped up. You can see the front is taller than the back here. That's where our timing belt goes for to connect the two lead screws that we have that will be involved in tipping. And you'll see that assembly a little bit later in the presentation. But that's why it's stepped that way. And then the frame is made out of extruded aluminum and wood. And the top is where our electronics are housed, and we've been calling it the attic up there. And then it's mounted to the drawer shell using slot bolts. So 80-20 slot bolts that go into that extruded aluminum, and then a screw goes through that way to keep it all tightly connected. So this is the full assembly. You can see this part is the the drawer shell that we talked about before with the drawer inserted. You can't see, but it is stepped. These are the two lead screws that are connected via the timing belt, and so that allows it to pass through there with the stepped design. The order that we did this was that the drawer shell and the frame were constructed, and then they were put together after that. So we drilled all the holes we needed to mount any electronics and mechanical components, and then the drawers and motors, the drawer and the motors were mounted into place. After that, we mounted all of the other components like the lead screws, motors, any like bearings that we needed for that motion. And then the attic space was mounted. So all of this electronic business on top here, that was all mounted. And then we added a slot in that top part so that the drill bit could actually fall through. So that's the order that we did that.
Thank you. So in our final design, we have a pretty good amount of 3D printed components. The first one is where you actually put the drill bit into the system. So that's what we've been calling our slot. So you can see it over here. On the right there is where you put the drill bit in, and then it also has a mounting point for the camera. And the angle on this slot allows the camera to look directly down into the drill bit while it's in the tray. So the slot also puts a little bit of distance between where the movement is actually taking place in the machine and where the person's inserting the drill bit, just for safety reasons. Another 3D printed component we have is this black piece right here. It's what we've been calling our shroud. So this goes over the tray. It has two LED lights mounted into it to provide more of a uniform lighting conditions for the the computer algorithm. And it also helps prevent the drill bits from actually falling out of the tray when they're inserted. So it just makes sure that they get to where they need to be. And then finally, well, not finally, but next we have this tray, which is the pink part right there. And so that's used as the platform for both the image processing and actually moving the bit to where it needs to go. Over here on the right, we have our tipping rod collar. So this mounts directly onto a lead screw nut, which actually moves up and down the lead screw. And then the rod simply slides into place on the tipping rod collar in the hole there. And then we also have our array of bins that the bits get sorted into. So we have two different kinds. They're shown right here. This bigger one goes towards the front of the drawer where there's more space, and the shorter one goes in the back. Both of them have this angle on them to kind of guide the drill bits into place and make sure none of them get put in cockeyed. And then they also have, this shorter one has the walls that have been trimmed down, and what this does is it allows the tray to actually tip down further without interfering with the wall of the bin. As far as the moving components and motor goes, we have three main ones. We have our gearbox, which is what we've been calling a right angle gearbox, our main lead screw, and our vertical tipping lead screws. So the right angle gearbox transfers rotation from a vertical axis, transfers the rotation from a vertical axis to a horizontal axis, and that's what actually connects to the main lead screw to drive it. It was assembled with parts from Servo City, and it's connected to one of two stepper motors that we have in the design. The main lead screw is just what holds the tray, sends it back and forth. And then we also have these two vertical lead screws. So this is where the tipping motion actually comes from. One is driven with our second stepper motor, and the other is driven via a timing belt that goes right down on the bottom here. So this way, both of the lead screws are driven together, and it has that tipping rod go up and down in one motion.
This is our main electrical diagram that we've been using for determining the layout of our project. It might look similar to things that we used in previous presentations, but we trimmed it down in order to show basically what we used at the very end of our design. At the very start of the layout, we have 120 volts AC coming out of the wall, and we're stepping that down to 12 volts using an AC to DC converter. We're stepping that down again from 12 volts down to 5 using a buck converter. 12 volts is being used to power our stepper motor driver as well as our two motors, the tipping and horizontal motion motors. The 5 volts is being used to power the Raspberry Pi, which controls the stepper motor driver, controls the LEDs which are used to light up the tray, and controls the camera.
Next, I'm going to be explaining the image processing algorithms that we were using. We begin the image processing by I apologize. So image processing is going to remove the rough edges on the drill bit caused by highlights and shadows. We do that by sampling the pixel width after that of the image taken, and the maximum width of the drill bit is then stored. And then we compare that pixel width value to the stored values corresponding to the different size drill bits. And then the motors drive the lead screws to move the tray to tilt the drill bit into the corresponding bit. Here is a couple of pictures that show the different steps in the image processing. On the far left here, you see an empty tray with no drill bit in it, and then at the bottom you see with a drill bit in it. We convert both of those images into black and white, and then we take one image and we subtract it from the other one to get that image at the top right-hand corner. And so this is mostly just an outline of the drill bit with some shadow on the left-hand side and highlight on the right. And then we use morphology to eliminate the shadow and the glare on the right to get that mostly rectangular shape at the bottom. And that's what we're using to find the pixel width of the drill bit.
So for our motor control, we're using an A4988 motor driver and a NEMA 17 stepper motor. We have two of these each. And then we control our step and direction with the motor driver, which is powered by our 12 volts, which we said before. And then this motor driver is set at full step mode, which allows for the fastest amount of motion, which is what we need. We don't have to be as accurate as some other things. And so the max speed we were able to get out of this was 7.14 rotations per second. And then this is after the doubling up from the gearbox. So it was half that coming out of the motor and then doubled by our gearbox. And so then for our motor code, we had two variables that were for setting the trigger for stepping the motor, and then we had one for the direction the motor would go. So at the top of this, you can see
setting the GPIO output to low is letting it know to rotate in a counterclockwise direction. And then it jumps into this for loop, which the 0 to 328 is the amount of steps taken. And so it just goes through a set of setting the output high and low and having a sleep amount of time, so the motor can get through its full motion. So the 5 steps to our motion is pretty much this, just copied 5 times, other than for jittering the bit out when it's tipping it out. That is just set into another loop that jiggles it about 15 times. So for our prototype testing, these are some of our main SDRD requirements that were tested and that we were close to getting but didn't quite get there. So we needed 12 bins at the beginning, but we only had printed about 6 or 7. And then for our size, our 16 by 16 base was just 0.2 inches off because we didn't account for the handle on our drawer. And then for our budget, we calculated that out to be about $25 over budget, which our budget was about $100, or the selling price of this was about $100, and then we were $25 over that budget to create the whole device. And then for our sorting time, on average, we were off by about 8 seconds. For the closest bins, we were about around 11 seconds, and for the farther ones, we would hit around 18 or 19. We wanted this to be around 10, which we will improve in the future. And then for accurately sorting our drill bits, our system was almost completely accurate on sorting black drill bits. We only got, I think, 1 wrong on that. But when we tried sorting gold drill bits, it was sizing them about 1 size lower, so we still need to improve upon that. And then for some improvements we'd like to make for our motor section is to add some more ceiling height to our device so we can have more room for tipping, and then that would eliminate the need for our jitter function and then allow us to have more time. And then we'd also like to add maybe a stronger motor so we could also translate it at a quicker rate. And then simplifying our code by adding more functions so we weren't just copy and pasting code, and so it would be a lot easier to read and work on. Other improvements that we can make on the electrical side, we said that we would have indicator lights as sort of a user interface on the front of the machine to let the user know what step, what stage in image processing they're in. Right now we're just printing out print statements on a monitor, and we would rather not have that, not resort to that. We need a fuse to protect the Pi from the power coming in from a wall outlet. And we need a drawer switch to let the machine know when the drawer is open so that we don't have the machine sorting drill bits when there isn't a bin to put the drill bit into. We don't want the drill bit getting stuck or anything. Right now, we have 2 power cords running from the wall outlet to the machine, and we would rather consolidate that down to 1. And on a related note, we want to clean up the wiring on top, and we would always like to improve the speed of the system. And to do that, we could add an additional sensor by the shroud to let us know when a drill bit has been dropped in, because right now we're just looping through and doing the image processing over and over again. And so if we know the exact moment that the drill bit is dropped in, that could reduce our time by about 5 seconds on average. Some lessons that we learned a lot on the electrical side. We learned a lot about Python and various Python libraries, especially ones specifically for computer vision. We learned a lot more about how the Raspberry Pi works and different issues that can crop up when working with the Raspberry Pi. We learned about consolidating different subsystems, like taking different systems and then getting them to fit together effectively and efficiently. And we refined our knowledge of computer vision algorithms and learned how to more easily tune different values in order to get the most out of the different algorithms that we used.
On the mechanical side of things, one of the main things we'd like to improve is ease of assembly. So every time a part went wrong, something got loose, anything like that, it was kind of a big ordeal to get our system disassembled and then reassembled and make whatever correction we needed to. We'd also like to reduce the number of parts we use in our tipping system. So I described that with the timing belt and a pinion and 2 lead screws. And the right lead screw actually has a lot more components involved with it, and that eventually led to some issues with the lead screw spinning inside of the coupler and just the system getting loose. So consolidating that would be very helpful. We'd also like to improve the motor mounting techniques, particularly our main lead screw motor is a little bit wobbly right now. So we'd just like to make sure that that's rock solid. And then adding a cover over the top of our project for more uniform lighting and also for safety reasons. This way we can put something on top of it, have it be blocked from any sort of hands or anything like that, but also still be available for viewing by the user.
Okay, so some of the lessons that we learned while we were working on this project, Jack alluded to this a little bit, but putting flats on lead screws actually really helps when putting into a coupler or anything that has a set screw. Flats help a lot so that doesn't spin in there. Having 2 people review CAD designs before ordering and fabricating parts. So this was a big one. When we built our right angle gearbox, one of the group members actually flipped which gear was in which place. And so one of the gears we budgeted for being shorter was actually a lot longer, and we had to cut off part of the gear, which removed the set screw, so we had to press fit that onto a rod. So it was a lot more work than it needed to be. So just having people double check that is pretty helpful. We learned that the hard way. And then the cheapest isn't always the best alternative. We learned that pretty quickly too. We actually got secondhand a set of drawer slides that we wanted to use, and they were almost as old as I am. We thought they would probably work and it would save a lot of money, saved $10, but wasted a lot of time, and then we ended up having to buy drawer slides anyway. So just, kind of a takeaway from that is just don't cheap out if you don't have to, which we didn't have to. And then general hardware knowledge is another thing that I personally learned, at least. The different types of bearings or different couplers, how they work. Lead screws are different than just regular threaded rods. I didn't know that until I started working on this project. So just some more mechanical hardware type of things are something that I learned while working on this project.
And some of the other miscellaneous or other lessons that we learned that might apply to the career, or things that we used a lot in this project, involved really some of the most important was that parts and procedure documentation was extremely important. And if we didn't know what we were working with, we weren't really getting anywhere with it, and we'd basically have to go back to the data sheets on things that we didn't know about. We really had to put into play that hours of planning could save weeks worth of work, and we wasted a lot of time having to go back on decisions that we made without planning, and a lot of that initial design really sped up the actual building parts of the project. We really wanted to play to the strengths of the team. It's something that we identified at the very start, and that we also wanted to identify some of the weaknesses that we had, just so that they didn't cause issues later on in the project. And overall, we had a fantastic time working on this. Another thing is that if we came across a solution or a method that wasn't working, the best thing to do would probably be to evaluate whether we should even continue with it, and, or if we should go back to the drawing board and find something that actually worked better. So throughout this presentation, we talked about our project objective of what our machine was supposed to do. We talked about the overview of how it worked and what it was doing. We talked about the mechanical, electrical, and computer subsystems. We went over the prototype testing and some of the proposed improvements that we wish to put into place if we were to do this again. And we talked about some of the lessons learned throughout this project. Are there any questions?
You have selected vision system to detect which drill bit to use, and probably have multiple solutions, but you did the alternative solution analysis, and it was the vision system. Now, after you run through the fabrication and manufacturing those systems, do you think a better system could work better? If you want to redo the project, you consider other solution for this, or you're happy with the vision system you have?
So the question was, when we conducted our alternative solutions analysis, we considered other methods of determining the size of the drill bit and sorting it that way. So the question was, would we, if we could go back and choose again, would we pick the same method of sizing our drill bits? And I would say yes, I think we would. A lot of the other methods that we considered were mechanical. So if you've ever seen any sort of like sorting machine where it's various size holes and you kind of gloss them over the smaller ones until it finds the one that it likes and it falls into that. That would have been really hard to tolerance, I think, and we are going on pretty small increments between the drill bits. So I think computer vision was probably the most refined and size sensitive, I guess, method of determining the size, and I don't think we would change that.
One of the things that we probably could change is the method that we were using when using computer vision. We eventually got stuck in doing one way, that the camera would be mounted overhead, taking a picture in that way, and there's probably a better way to analyze the image from a different angle or perspective that's more consistent.
I'm actually curious about your mechanical system, and if you had the chance to start over again, would you use a lead screw and a stepper motor again, or do you think you would change that strategy?
Oh, here, I'll just stand by you.
I think the lead screws ended up working very well for us, especially the main one with the translation back and forth. That one works excellently. The problem ended up being with the one that controlled the tipping rod. So we actually talked about maybe we would still use like one lead screw, but potentially on the other end we wouldn't have a second one, so we wouldn't have to deal with the timing belt system. Maybe just having some sort of like linear bearing that would hold the tipping rod at the other end and just allow it to move up and down. I think that is probably the area where the lead screws kind of came up short a little bit, and that might be a way to address that.
If there are no other questions, thank you. Yes, thank you.
Is there a mode where you can make it bigger? No. It doesn't auto.
Nope. I'm going to set up a timer here. Yeah, because the person speaking is standing right here. Right, whatever, it doesn't matter.
The way which I was figuring is actually the same one there and the tablet over here. Because we're going to be demonstrating off mics. This one? Actually, the computer.
He's got the camera pointed here the whole time, so I was thinking the next person.
The camera doesn't move?
It wasn't moving last time. Yeah.
So like, what's your field of view? So I'll zoom on wherever you guys are standing. Okay. So don't worry about it.
Okay if we're on both sides of the screen?
Yep.
Okay. Right here right now.
That's what you just said.
So I'll be panning the whole time. Okay. You guys know what you're doing with the mics?
Yeah.
Just pass them over there.
Yep.
So you're not
So during Q&A, just remember that you don't have to pass the mics, just stand next to someone with a mic. Make it easier.
Good. Good. So hello everyone, my name is Tyler Matulis, and I'll be presenting today along with Ashton McAvoy, Matthew Bedell, and Sam Grossnickel. And we'll be presenting on behalf of Sherlock Holmes and presenting to you our final design for the smart lock that we've made. And our advisor is Professor Will. So today, like I said, we're going to be going over, I'll give you a project overview, and I'll also provide you a little bit of information of what our final design is and how we got to that point. And then at the very end, we'll share with you our budget and some of the lessons that we've learned throughout this project. So as a little bit of review, our design requirement is that we'll have the Sherlock will retrofit onto a deadbolt door lock and be able to remotely lock and unlock the deadbolt. So right here you can see this is basically the full project overview on this chart.
Right over here, you can see this is over here is the onboard system. So this is what's actually on the lock. You can see this is the brain, the microcontroller, and here are the sensors and the stepper motor. And then over here on the left side, we have the part that's on the outlet, and this is just a Raspberry Pi that connects the user interface to the microcontroller that is on board the Sherlock. So to go further into some of the mechanical systems, most of these haven't changed. From the start, we were planning on using command strips, and so far those have worked pretty well for us. Part of what was in our SDRD is that it couldn't leave any marks on the door. The command strips did end up leaving some marks on the door, but that's also probably because we didn't put a finish on our doors, we just put stain on it. But usually command strips don't leave any marks. And then we're continuing to use the NEMA 17 stepper motor to drive our gear train, and also the turning mechanism, which everything in here is 3D printed, including the housing. And most of that hasn't changed throughout the project, aside from small modifications throughout. So when we first started designing the housing, it was basically just kind of a skeleton to get a basic idea of how we were going to design the full project. So some of the modifications that we had to make throughout were, for example, we initially just had this being a flat plate, and it caused a little bit of wobble in the gears when it was turning. So we ended up extending down this collar right here to keep that shaft from wobbling in there. And also one of the problems that we had was right in here, this sheared off at one point when we were first trying to use it, because the 3D printed material wasn't strong enough to take that shear force. And so we added that fillet in there to eliminate that stress riser. And then also, as you can see back here, can't see it good from this angle, but you will later, there's basically like some spacing material in there to allow for the wires to run freely behind the motor here, connecting the Beetle to the Bluetooth module and the stepper driver, which are on opposite sides of the motor. And then also it provides some spacing for the batteries, which are housed back here between the battery cover and the motor, so that they don't contact the wires. And as you can see up here, this extends upward to prevent the batteries from colliding with the gear train right here. And then here's a little video that shows the operation of the gears and how this contacts with this internally. And that's how it comes together. And so now I'll hand it over to Ashlyn to speak about some of the electrical systems.
Thank you, Tyler.
Yep.
So to go into some more of our electrical subsystems, most of them have not changed. However, we have had some modifications. Initially, we were using the magnetic contact switch as our door shut sensor, and we were using our Beetle BLE as our onboard microcontroller. However, the Beetle BLE does not have standard Bluetooth on it. It does come with Bluetooth, however, it doesn't like to play well with other devices, so you need another device made by that same company in order to access its Bluetooth. So we ended up using a Bluetooth module, which is the HC08, on board our housing as well. In terms of sensors, we were originally going to use a potentiometer, and then we changed to a Hall effect sensor. And finally, I'd like to talk about the stepper motor driver and the batteries. The stepper motor driver we had initially planned on would unfortunately not work for us, so we needed to choose a lower voltage stepper motor driver, as seen there. And then finally the batteries. We had initially chosen the CR123A batteries in our system, however we determined that they wouldn't provide us the necessary capacitance that we were looking for, as well as the voltage is at 3 volts in our system. Will work at 3 volts, however it cuts off at about 2.8, so if there's any dissipation in those batteries, it will cut off pretty quickly. However, through the process, we switched to AA batteries and then determined that the AA batteries could not supply enough current to actually turn the motor through the stepper driver. So then we switched back to our original Panasonic CR123A batteries. And I would just like to note as well that we did determine that there were other batteries that we would like to use. However, because of cost, the batteries themselves would be about $10 a piece. Along with the charger and the holders, everything would be about $70. So to save some money, we decided to go back to our original Panasonic CR123A batteries. And we are using 2 of them in parallel and then in series with each other, so 4 batteries total. So now I'm going to talk with you a little bit more about our user interface. And so just to reference back to the initial chart that Tyler had gone over, this is this portion up here. So the user interface has taken many different forms. As we mentioned to you in previous OPRs and presentations, we were originally going to have this be an application on your phone. However, we switched that to a website. And we did that for various reasons, the most predominant of which being we were going to code it for an Android device. However, as I previously stated in previous presentations, Professor Johnson and his wife, Professor Johnson's our customer, they both have iOS devices. However, app development for iOS is significantly more complicated than for Android development. But with a website, you are able to access it on your mobile device, and you can even make an app on your home screen of that website. So it just gives you more usability. You can access it on your computer, or you can access it on your phone. So this is just a snippet of what our login screen will look like. So we have the Sherlock logo there and then the login screen. And so when the user clicks log in, then you see this field, and each user is given their own unique username and password. And then they can hit submit. And once those login credentials are deemed to be valid, then the Beetle becomes activated on our system. Normally it is sleeping. However, we set a global variable in our code to connect to the Beetle once the login credentials are deemed valid, and so that would save us some power there. My apologies for this slide. It did look better earlier. To talk a little bit more about our Bluetooth protocol, we had set various bits here. So we have entry bit 0A and 0B being the exit bit, and then the numbers in the middle that are blue are what's important. So the 0A, 03, 0B responds to the shut and locked position. And so that's determining that the door is shut and also that it's in the locked position. So we use a door shut sensor, as I previously mentioned. And so the door can either be ajar or shut, and then locked or unlocked. And so all these numbers amount to our Bluetooth protocol. And our Beetle is sending out those numbers, and then our Pi reads them in as strings and then accesses a dictionary that was created on the Pi that will then display to the user on the website whether the door, what the status of the door is. So now to talk a little bit more about the Beetle and all the stuff on board the housing, I'm going to hand it over to Matt.
Thanks, Ashley. So I'm going to discuss more about what is actually the device. What are the actual devices that are on the door? As Tyler previously mentioned, we are using 2 proto boards that are on each side of the motor. I'm going to first discuss the first proto board, which has our Beetle, our door shut sensor, and our lock turn sensor connected to it. And so this is a pinout diagram of the Beetle. As you can see, we use 5 volts to wire over to the other side to control our Bluetooth module. We use our analog inputs to detect what the current status is. The shut sensor and the turn sensor are specifically inputs that then the Beetle will read to then determine, okay, what do I need to send back to the Pi, which then tells the user what the current status is of the door. We also are using pin A1 there as a sleep pin. That was alluded to earlier of the stepper motor driver, and the stepper motor itself is the main current draw of our system. And so we needed to have a specific way to be like, hey, we need to shut this thing off because otherwise it's going to kill the batteries in hours. And so we have a pin specifically to do that. On the other side, we are using our digital inputs and outputs to control the transmitting and receive with our Bluetooth module, as well as to control our stepper motor through our stepper motor driver. The beauty of using this driver is that we can use it with 2 pins as opposed to 4 pins that we would normally take if we were to do it manually through a microcontroller. And then the V in and ground on the bottom of our diagram here are specifically connected over to our batteries, which, as Ashlyn alluded to earlier, are 2 in series, and then those in series are in parallel to get more capacitance, which gives us a grand total of 6 volts running our system. Next, I'm going to talk about our other side, which is our other proto board, which includes our Bluetooth module, the stepper motor driver, and the stepper motor itself. The connections are effectively the same. They just have the same names, just going back over to the Beetle to let you know, okay, this is what's coming into the pins on this side. Specifically, the thing that is not shown here is across the voltage and ground on the stepper motor driver, we have to include a 100 microfarad capacitor. If you don't, there can be voltage spikes that will then short your device, and you will have to redo all of your soldering because you had to take out that stepper motor driver and replace it, which is obviously a pain. But otherwise, everything else is run the same. We have our 5 volts that are coming to our Bluetooth module that are both enabling and powering the device. And we also have, which that has to be constantly on because it's obviously checking constantly to see, hey, am I receiving anything from the user? And then there's our sleep and driving pins going to the bottom of the driver over there. It's the same with the motor being attached to its pinout. Now I'm going to show you a few more of the actual photos of the finished product. This is a close-up of one of our proto boards, trying to sneak in around the side of the motor housing to show you kind of how we soldered in and how tight of spacing it had to be. It's because of size constraints due to our SDRD, there had to be a lot of kind of squishing of wires to get it perfectly into the right spot. Yeah, and so that's kind of that one. And then more specifically, this gear train photo, you can see that there is a magnet attached to the driven gear. And so to go more into the, I guess I don't want to say the most important part, but the crucial component of our entire device is how do you know when the device is actually fully turned or not? And so what we did is we attached 2 magnets to the actual driven gear side of opposite polarities, and then attached them kind of at the start and end of what a typical door would be in terms of its turning radius. And then we have a Hall effect sensor which detects, okay, what kind of polarity am I reading from a magnet on the other end? And so when it is locked, it is showing one polarity. When it is unlocked, it is showing the other polarity. And there's a calibration mode to know, okay, for this specific lock, I know that this value is its locked position and this value is its unlocked position. The user will then interact and use that calibration system to then get a different turning radius on each of the different types of locks that it needs to accommodate. And so then I will hand it over to Sam to discuss more about the final product.
Thank you. All right, I'm going to stay on this slide for a second, just to point out our 3D printed gears, and then this wedge was used to pass the motion all the way out through the front of the front plate so the user could turn it manually. And we didn't really have any problems with the gear tooth design. It's the standard gear tooth and involute design, and so it meshed really well. And even the PLA gears were strong enough to withstand everything that our system was experiencing. We didn't have to go up to nylon, which was nice because you get to print PLA for free as opposed to nylon, which goes in your budget. And then here you can see something else that went in our budget is a close-up of the arbor, which attaches the drive shaft of the motor right here by a set screw to our main drive gear, and then is held on by machine screws and nuts, and that made a more secure mechanical connection as opposed to just press fit onto the shaft of the stepper motor. And we didn't really have any issues with that once we tightened all the set screws down and everything meshed and turned pretty well. Another thing that we have a picture of here is a piece of hardware that we added to the project, or at least the casing that we added to the project a little late, but we got it done with an acrylic laser cut design, and so I was able to just go look for existing Pi Zero laser cut templates online and kind of defeature with the help of other students. Defeature and expand the sandwiched design here, and then use some M3 screws to go through the clearance holes on the Pi circuit board itself, and then allow for extra ventilation, and then make sure this power cord didn't kink. So that's why we have a little bit of extra room here. We didn't know quite exactly how much room this needed to go without kinking. And then another little fun bit is I was able to get Sherlock Holmes laser etched onto it, so kind of made it a little fun thing. And then it's just super glued onto the back of an AC adapter, and it pops on the wall just like a CO2 monitor, and just sits there and should run from boot, right? And then here's a picture of the finished housing with everything in there, but you can't see that, with the battery cover on the test door, and you can see the bolt is extended, the deadbolt, and this is the fob that the user would turn to manually activate it from the inside. You can still, from the other side of the picture, actuate everything with the key, no problem. And this pink on the top pops off, and that's your easy access for the batteries. And then that would only have 2 screws here and on the opposite side, and then the faceplate is supposed to have about 4 screws to get at it if you need to get into the guts of the gearing. But even with just the battery cover, you can even access the Beetle for if you need to recode anything, let alone batteries, and access the wiring pretty well if you need to fine tune anything. And then I would like to step over to the budget and address the overall lot costs. Total development costs that we have that we had to pay for was $220, and we're looking at around 50 for mechanical, almost 90 for electrical, and 80 for connectivity. But that does include doubling up on many components for redundancy if we have had any issues during product development, including burning out stepper motor drivers with the wrong capacitor, which did come in handy. We had 2 Pi Zeros, 2 stepper motor drivers, and 2 Beetles, and that inflated our cost here considerably. But when you consider all that went into the housing that the customer would receive, it's only around 112, so you'd call it 115, and that's pretty competitive, even considering margin with market available similar systems that would be around $200 MSRP, so not too bad. And then I would like to touch on some lessons learned from this project. And a main one for me, we each kind of like had favorite ones, and so I'm just going to go through them pretty quickly, I guess. Sort of looking at the project work scope and the workflow that the project will encounter, a key thing for me would be to try to identify bottlenecks in what's going to hold us up, and then to help alleviate those issues, try to offload as much as you can from those resources, whether it be, you know, helping someone code, helping someone troubleshoot, or helping someone in a SolidWorks software that they're not familiar with, anything like that. But just keeping an eye out for where the bottleneck is definitely key. And that being said, testing system integration early and often would be something that we would take moving forward. Leaving troubleshooting to the very end and debugging didn't pan out excellently for us, and having more on housing sensor placement testing would have definitely benefited this project immensely. And then we didn't have too many problems with 3D printing, but when you do print early, print often, you just have to allow for issues to occur when you're working with the printer bots that have had hundreds and hundreds of hours of use without a rebuild. And we did get quality parts out of it, but you have to keep an eye on it, kind of babysit it, and expect like a failure every third time. So another point that we learned was to perform more thorough ASAs and research on your components. A critical one being, I know that Ashley wanted me to mention, was the Beetle had non-standard pin sizing, so it didn't just slot straight into the proto board, so they had to drill it out. That was kind of a thorn in their side. Another was we bounced around with our power battery situation, and that slowed our ability to get through troubleshooting quickly enough. But other than that, it went pretty well. And so in summary, we went through a project overview, showed the final design and our path to the final demo, touched on some budget, and covered some of our key lessons learned. Are there any questions? Yes?
So you mentioned the 3D printed gears. Did you do testing to see how much force they can withstand? Especially if thinking about when the user manually turns. If they turn, you could force the lock once it's already open or closed.
Yes, so I was there to break gears, and where I broke the gears, the question was, did we have any issues with the gear teeth specifically? Yeah, so if we get here, we found the weak point is not at all the gear teeth. The in-volute design is pretty standard, and we didn't really have any issues or gear teeth breaking at all under any of our loading conditions, even when the motor was trying to turn against an either fully open or fully locked. So our breakage occurred at that point, that weak point with no fillet. And so once we filleted that, everything was more than strong enough to withstand all the forces on the deadbolt actuation. Anything else?
Any other questions?
Well, in the demonstration last week, you had some clicking sound while rotating. Is this something expected, and if it's gonna cause any issue in the future if you excessively use the lock?
So the question was, in our demonstration that we had last week, we had some issues with some clicking, which was actually the gears slipping, the stepper motor driver slipping a little bit, and what kind of issues is that prompting? The main issue that's prompting is, as you saw with our what's the word? Presentation last week, was if it does that, what it means is that it's hitting a torque point that it's struggling with a little bit, and there's enough play with the gearing currently that if there's not something holding it down, it'll pop off of the actual lock itself, and then it'll turn continuously forever because it's out of alignment. And so when we put on the cover housing, which is shown at the top there, it will actually stick them together, and so the clicking will no longer be an issue. It'll just keep pushing until eventually it gets through, and then it'll complete its rotation, get to the sensor point, and be done.
Another piece of that sound is just the actuation is stepped on purpose. It's waiting for sensor feedback, so it does sort of click through its motion. It's not just a smooth motion because it's looking for sensor feedback to stop the motor. We're not just counting steps. It has feedback from the sensors, and that's what it's waiting for.
Any questions? Cool. Thank you.
Thank you.
We'll take a 5-minute break. Be back at 11:30. 7:30.
Over or not over?
Over. And really 21 something.
21?
Yeah.
That's fine.
How do you take that off? Oh, yep, make sure mute on top. Okay.
Only go on.
Watching videos on Tuesday, and that's it. Yeah,
Did you check Elvis?
Yeah, I checked them. Yeah, I checked that.
I want to just see how just very quick.
Okay, when we're ready, when I hit mute button.
Here, do you want to put your phone on that side?
Oh, yeah. My phone's going to be here. When I start talking, let's start. It's silent.
Yeah.
Oh! No, I don't think. No, I should. We should be good. I'll make sure. We're having a problem. Auto lock, never. Yay. Yeah, go to settings. You go to passcode lock. Touch ID and passcode. So, wait. No, wait, cancel. It goes up. Display and brightness, there it is. Auto lock. Never. Hey, Rita, you want to close the door? Oh, I didn't notice that. He doesn't want to see his own group present. Hey, you want to grab the door?
Thanks, you're real.
We good? All right. Hello, everyone. My name is Alex Groth. I'm here with Bradley, Shirley, and Rita presenting on behalf of the Quiet Coffee Grinder team our final oral report. Our advisor is Professor Elhawayek. To start off and give you an outline of our presentation today, we're going to start with a project overview, and we're going to tell you our problem statement and definition so you know why we designed it the way we did and what our project is. We're going to next go into the manufacturing that we did throughout the semester, and that'll be broken up into two parts, the 3D printed parts and then the machine parts. And after that, we'll go into the electrical side of things, starting with the printed circuit board that we have and how that fits into our control box, along with the other wiring. And then we'll go into the Bluetooth and mobile application that can run the device. And lastly, we'll talk about the testing and some of the requirements that we didn't meet, and then we'll open up the floor to questions. So to start off, our project overview, this is our problem statement. It is to construct a functional coffee grinder that produces minimal noise while grinding finely ground beans in a timely manner and putting those into a removable container. And now into the manufacturing. The first 3D printed part we did was the lid. As you may remember, that attaches to the top of the PVC container. And after this was printed, we had to add a few attachments that allowed that to be done. The first were the 3 latch hooks on the outside. They're equidistant apart, and these were screwed into the side of the lid. There's a little flat edge that allowed that. And then the next thing is the O-ring. There's a little ledge that the O-ring was placed on top of, and this will allow an airtight seal when the latches are squeezed down. It'll squish that O-ring and allow for a tight seal. And then lastly, the sound insulating foam. As you know, that was the big thing that we used to dampen the noise. And this sound insulating foam was attached to the bottom of the lid so that when it was placed on top of the container, it was a flush of the foam all the way down. The next 3D printed part was the grounds container. And this is very similar to the lid and the attachments that were needed afterwards. Again, it used the latch hooks that attached or would latch to the PVC. Originally, we were going to have those higher. It's kind of hard to see, but there were some, again, flat edges that those were supposed to be attached to, but it was a little too far in, and with the curvature of the PVC piping, it wouldn't allow for it to latch in tightly. So we moved those closer to the edge. The next thing is the rubber sealing. It was a weather stripping, and that is attached around all the edges so that when it is clamped in, it again has an airtight seal and doesn't allow the sound to escape. And just like the lid, there's also sound insulating foam on the inside, preventing and reflecting that noise back in as opposed to out. The last two 3D printed parts are shown here, starting with the ground chute. The first picture is a top view when it's fully assembled, so it's kind of hard to see what it exactly looks like, but next to that is a CAD model. So after the beans are ground in the burr housing, there's a slot in the burr housing that allows it to leave and then go into that slot in the chute, and that will then lead straight to the grounds container. The last is the IR sensor mount, and this is attached to the base plate just in front of the motor where the grounds container would be, and the grounds container would slide in and be just in front of that, so the IR sensor would be able to see into that. And the two LEDs, the IR LEDs, are bent at a 90-degree angle to fit into the hole in the grounds container. And as you see, there's a hole in this part. That is to bolt in the IR sensor to hold it in place. There's also a hole that lines up with that on the IR sensor itself. Now on to the machine parts.
Okay, the first machine part is our motor clamp. Here's our old design of our motor clamp, but it's kind of overcomplicated because we only need the motor clamp transfer heat, so we don't need it covered exactly the shape the motor is. So we changed it to our new design. It's basically like a calendar, and after we machine the calendar, we cut in half and connect those two with hose clamp. The reason why we did that is because we don't want motor clamp hold the motor too tight or too loose. We want it adjustable. You can see these dots here because at first we want use screws to connect these two parts, but these screws are too tiny, so it's hard to draw those tiny holes on the side. We even broke one too, but great. And next machine part is burr housing, and we made it by aluminum. It's about 0.2 thickness, so it's really thin, and we hand machined the whole part, but we did this opening with CNC machine. And our burr housing lid, this one is our top wheel of our burr housing lid, and here's the side wheel, and it is our upper burr. We need those 6 screws that matches on this surface. But at first, I don't think it's hard to do, but I failed 3 times. First one, I drew bigger holes than screws, and second one, it won't match perfectly. So I asked Dave to help me locate those holes, and it finally works. And we also need to match the diameters with the hopper and the burr housing, so that we also change our chute design for it, because our old chute is like a ring around the burr housing, and we change it to just cover the opening. And our distance between the two burrs is it's fixed. It's only about 0.01 inches, so it's designed for medium ground. And this is what we check online. That is for most coffee beams. And for our base, here's the braid wheel for our base, and you can see that those screws are really flat with the surface. Because we draw it, we use our big drawer first, and we use smaller one to draw it deep enough so that our screws will going into the surface and not on the surface. And we use that thick vibration format because we test it, and it will be much quiet than it's attached to the table without any format. But those vibration formats are really sticky in both sides, so we use our sound isolation foam to cover it. Yeah, and then transfer to Bradley to talk about electrical.
So now I'm going to start talking about our PCB design. This is just kind of to illustrate, this is what it looked like on the breadboard. Kind of messy with the wires, just going up and over on the board. This is our final circuit design with this. Yes, the wires are a little bit messy, but this will be inside a control box. So it will hide everything except for these 3 LEDs and the push button. So just to give you a little bit overview of what everything is, in our final design, the on-off LED will be the green light. Our hopper being empty, the indicator for our hopper being empty will be the yellow light. The grounds container LED light will be this red one. It's a little hard to see, I can tell. Just for reference, this is our ground. This is where our power source is. This is our power button to turn on and off the motor. And these two these two resistors right here are where our Bluetooth for transceiving and receiving signals are. To talk about more of the relay, one of our biggest problems was the connections right here. The wiring on these wires right here that go directly into the wall are too thick, so every time we would move it around stuff, the wires would just pop out. So I went and visited Bob Sokol, and he worked with me to get a couple extra wires that we could use, and then put this together so that we wouldn't have that issue, because it's 120 volts and we don't really need that. After this, though, we are going into one of our next steps to do before the excuse me, before the design expo is to get the AC/DC converter also connected onto the wire in here. And to show how I'm going to do that is that we are going to splice the wires right here, and then have two small wires to connect directly to the power source. Because currently we have two separate plugins, and this is really inefficient, so you'd have to plug in the Arduino first before the motor, otherwise the motor is just going to run. And so we want to prevent that and have the whole system turn on at the same time. So this is our final design for the control box. However, towards the end of the 3D printing, it did not print the bottom holes correctly, so we're going to have to print that again. So all of this messiness, which will be cleaned up more, is going to go inside here. And so that's our last step electrically to get all these components back in this box. For Bluetooth, we, towards the end, had a hard time with our Adafruit Bluetooth because it was so it had a pre-existing app that we were really excited about. However, to modify it was really hard, and when we looked into creating an app that would be compatible with it, we had many issues to do this, so this is why we switched to an HC06. And now I'm going to pass it to Rita to explain more of that and the app.
Thank you so much. So in this slide, I will talk about the features of the HC06. Actually, it's easy to use, and what I mean by it's easy to use, I mean like you can find a lot of libraries and a lot of tutorials that can help you to have a deep understanding, and it's easy to be configured with the Arduino. This board, it's operating on 5 volts, and it has a standard range of approximately 10 meters, and it has an indication LED in the side that it keeps blinking until you connect it, and when you connect it, the LED will become stable, and it's easy to build. Here in this slide, I will talk how to connect the Bluetooth to the Arduino. But before I start to talk about that, I will this is the block diagram. You can see this is RX, TX, 5 volts, and the ground. TX is represent the receiver, and the TX it's represent the transmitter, and 5 volts and the ground. Here, as you can see, the red wire it's connected immediately to 5 volts, and the black one it's connected immediately to the ground. And as you can see here, the green one it's connected to the transmitter immediately, but for the receiver it's connected to between 2 resistors. And the reason why it's connected between 2 resistors because we need a voltage divider, because it's required an output of 3.3 volts. And this is why you see here 2 resistors, one connected to ground and the other one is connected to pin D5. So actually D5 and D13, one of them represent the receiver and the other one represent the transmitter, sorry about that, transmitter. So, and these are not fixed because it depends on the library that you use. Maybe someone will use different library. This might be changed, and you might go to and try to figure out which input is the transmitter and which one is the receiver. Here, this is our application. This is how our application look like when it's not connected. So actually, when we want to connect to the grinder system, all what we need is to push this one, and when we push this one, it will show a list with the Bluetooth that is already wired with the phone. And all what you need to do is to find the HC06 and connect it. And here, what it's going to look like. You will see it's connected. So here, how to power the system. Actually, we have 2 ways to power the system. One physical switch, and the other one it's by the app. What I'm going to focus on this slide, I'm going to explain how to connect it by the app. All what you need here to do is to click this button, and when you click this button, it will send a signal to the Bluetooth, and the Bluetooth will send the signal to the Arduino to run the system. And it's the same. When you want to turn it off, all what you need is to click it again, and it will do the same process. And even if you use the switch, it will give a feedback. Let's suppose that the system is on, and when you click the switch, it will give a it will run on the motor, it will run off the motor, and it will give a feedback that it's on.
So in our grinder system, we have two IR sensors, one for the container and the other one for the hopper. For the container, actually, we adjust the code to check every half second to see if there is an obstacle. If there is an obstacle, all what it's going to do, the Arduino will send a message to the app to tell it that there is error, which means that the container is full. When it's full, it will stop the power, and we will not be able to run the motor anymore until we get the container empty or remove that obstacle. So for the hopper, it's the opposite of the first IR sensor. We make it, we adjust it to see if there is no obstacle. It sends a message to tell that the hopper is empty, and it will keep checking after 3 seconds, while keeping in mind we are still allowed to run the system. Yeah. System.
Going on to our test report, overall our system did pretty well, but there were 3 requirements that we did not meet, and they're listed here. First off, 80% of the grounds passed through a size 20 mesh. It failed that. Only about 60% of them got through. The next one is the decibel level is lower than 60 dBA. We were around 65 at 10 feet away, so it didn't pass that one. And then lastly, the hopper should hold more than 12 ounces of beans. The hopper only held 10 ounces, which is only 2 ounces less than that. And we didn't see these as too big of an issue. Obviously, the whole point of this was to make a quiet coffee grinder, and if we didn't make the sound requirement, that's bad. But we made a pretty low sound requirement, and originally, if you, the coffee grinder we bought at the beginning of the school year was around 95 when you ran it. So, I mean, we decreased it around 30, which is a good amount. And obviously, there's room for improvement, but it does sound a lot better than it used to. And then going on to the first one, although we didn't get as fine grounds as we wanted, the grounds we have are still able to make coffee, either through a French press or just a drip coffee maker. And then lastly, the last requirement we didn't meet, 10 ounces of coffee that the hopper, or coffee beans that the hopper can hold, still allows for numerous cups of coffee to be made. So although we didn't meet the 12 ounces requirement, it still is fine that we're at the 10 ounce because it still makes plenty of coffee. In summary, we started out with the project overview, told you our problem statement and what our project is. And then we went into the manufacturing, the 3D printed parts, and then the machine parts and kind of issues we had with that. And then we went into the electrical side of things with our circuit board and the control box and how everything fits into that control box. And then lastly, we went over the Bluetooth and how the app works and how you interact with the app and the system. And then lastly, we talked about the testing and which requirements we didn't meet. Are there any questions?
So I'm curious, you guys stuck to a pretty similar setup as a typical coffee grinder, right?
Yeah.
Now that you know this problem really well, is there anything crazy that you would try to totally change up the design? What would you do differently?
So the question was, now that we know what we know, would we change anything or what would we do differently? And one thing that, I mean, Professor Will had a good idea at the beginning is kind of have 2 motors grind it down to a smaller, but not as small as you want, and then grind it kind of 2 steps. And at first we thought our design would be cheaper and easier to do, but obviously it didn't meet our requirement. So one thing I think we would want to try is maybe try that idea out, 2 separate grinds, so you could run the motor at a lower speed and it'll be quieter than the high speed motor.
So you mentioned that you had the requirement for 60 decibels. What was the amount that you measured?
So the question is the amount that we measured. It was 65.
Like when you're measuring that, I'm sure you had a certain distance or how far away did you measure?
So the parameters, the question is about the parameters of the test. So in our SDRD, it was measured in a room that was below 50 decibels and 10 feet away. So the room we originally used was the FITES conference room. Then we used Bradley's apartment next because we thought that was more, we used his kitchen because that was more kind of where you would run it. And the FITES conference room is kind of echoey. But either way, they were both at 65, so it didn't really change anything.
And just to go a little bit more, that's a number we were getting consistently. There were times we could get down to like 62, 63, but there's so much variance in that that it was hard to pin it down.
Is there any directionality to it? or was it, you know, if you measure different ways around it, or?
So the question was about directionality of the decibel meter, and we did try that because I was curious about that. So I was kind of pointing the decibel meter all around at different angles around the room. I got the same readings. The distance didn't even matter too much unless you were like right up to it, as opposed to like pretty far. If it didn't come back, then it wouldn't run. So if it was out, it wouldn't come back. But the way we have it set up now is if there's any obstruction, then it shuts off. So then it won't shut off, or it won't shut it off if it's out of there. So that was something we didn't really think about after we changed the design. Any other questions? All right, thank you.
You didn't change more, right? Close it up again. Is that this one? No. No? Sure. Okay. I'm going to turn this on. Because you're going to... Turn it on, start the timer.
Hi, we are the autonomous go-kart team, and the team member is Jenwen Ma, Grant Jepson, Ryan Nuendig, Tristan Ranyan, and Paul Flay, and our advisor is Professor Yohoik. Today we will talk about the SDRD, steering system, vision system, system controller, braking system, test plan results, and the current state of the project. And after that, we will do the summary. For the SDRD, the device shall steer accurately 30 left and right or forward. Also, it should stop from full speed within 18 feet, and it should autonomously control the speed of the go-kart, and it should have ability to detect and navigate around the obstacles. Also, it should be driven manually and operate autonomously, and it should meet all of the power racing series and the autonomous power racing series rules, and we will ensure that the safety of the go-kart and its environment. For the steering system, our goal of the steering system is make it move left to right or right to left in less than 0.5 seconds, and it should steer 30 seconds from left to right accurately, and it should have 5 positions angle between minus 30 degree and 30 degree. And for the present condition, our go-kart can move left to right about 2.34 seconds on average, and the maximum angle on the left is 26. The right one is 27.5. And I will like Grant to introduce the design.
I'm going to be talking about the steering system a little bit. So as you can see, we are utilizing NEMA 34 stepper motor, which this is our sub-assembly, which is attached to the steering column. And as Evan said earlier, we are not obtaining the turning speed we wanted. We believe this is due to the fact that we're not utilizing the full frequency. This stepper motor has a maximum frequency of 6 kilohertz, and right now we're only using 2 kilohertz. With the time that we have, this is sufficient. If we had more time, we would like to fine-tune that and get that timing, and we believe that that could be a possibility because our stepper motor is spec to this. And then we're also using a potentiometer. The potentiometer provides feedback for our turning. It provides an analog from -1 to 1, -1 being all the way to the right, and then 1 being all the way to the left. So here you can see this is our steering control. So what happens is our Odroid receives distance signals from our LiDAR and our sonar sensors eventually, which we don't have those working currently, but we hopefully will. It sends it to the Beetle. The Beetle will say, either go to 1 or go to -1, and then the stepper motor will try to achieve that angle. We'll go to that wheel position from the stepper motor. It will turn it, and then we'll keep iterating that until we eventually get to our right angle, to our steering angle that we desire. All right, I'm going to hand it over to Paul.
Thanks, Grant. All right, I'm going to talk briefly about the current state of the vision system and the control system. So our goal for the vision system was to incorporate or fuse LiDAR data and sonar data. The reason for this is that the LiDAR, shown at the top right of the slide, is mounted to the front of the vehicle. This allows us to get a pretty good picture of what's in front of the vehicle, but we have severe blind spots to the side and rear of the vehicle. The idea of adding sonar to the sides of the vehicle was to help cover those blind spots and detect any obstacles or objects that might be within a certain proximity to the car. What has actually happened, though, is that was a little bit too ambitious. We do have housings. You can see them here again on the right of the slide for both the LiDAR and the sonar, and they are mounted on the vehicle. However, the electrical systems for the sonar are not implemented yet. We just don't have the connectors to plug into the Raspberry Pi. But for the LiDAR, it's mounted and it is connected, it has been connected to the Odroid, as we saw in the last demonstration, to the software and electrical system, control system. I'll pass it off to Tristan here to talk about the
Thank you, Paul. So I'll be talking to you guys about the system controllers. Starting off, we have the Odroid XU4. So this is the major system controller. Everything that happens here. The Odroid is connected to various devices and controllers that reads in information and then relays this to our neural network that's built on ROS, or the Robot Operating System, if you're not familiar. This neural network then takes this information and makes decisions and actions for the cart so that way it can navigate the course. The neural network is trained in a way so that way the information it receives allows it to make the decisions properly. Next, we have the Beetle. Simply, the Beetle reads in information from the potentiometer and also turns the cart. So how does it do this? how does it do this? The potentiometer essentially is mounted in a way to the wheel of the front left tire of the cart. So that way, as the wheel turns, it will give us a current position in the potentiometer. So the potentiometer turns with the wheel of the cart. Why does it do this? It acts as a feedback system for our steering system. So that way, if, for example, the cart turns left a little bit, it doesn't turn too far left and possibly damage the steering column. Next, we have our two Motina Megas. So the first Motina Mega is just simply a controller for our drive motor. The second one is connected to our first Motina using over wireless to act as a wireless kill switch. So that way you can start and stop the cart as we need. Oh, lovely. And then we have the Raspberry Pi Zero. So Raspberry Pi Zero reads distance data from all 6 of the sonars that are around the cart in order to give us an idea of the course, where the course is, and what objects are near our cart. I'll pass it on to Ryan to talk about braking.
So the next subsystem that we are going to talk about is the braking system. And the braking system that we originally planned on using utilized an Econ gear motor. It was a brushed DC motor that operated at 4 amps on 12 volts and was able to achieve a overall torque of 57 foot-pounds. We believed at the time we needed 27 foot-pounds to engage one brake. This rating is actually taken at max power, so 50% of the motor's duty cycle. Unfortunately, we found out that the gearbox and motor were insufficient for the forces required to engage the brakes. So we actually ended up splitting and shearing a couple gears. We pulled the gearbox apart, and there was a pinion that was completely snapped in half, and there were 3 or 4 teeth missing on a different one, and the motor was incapable of pulling one brake even when it was at 4 amps. It was able to only partially engage the one brake that it was attached to. So what we've done is we're showing the control system of the car. The control system has not changed in terms of the braking. We receive a steering and braking signal, or I'm sorry, a throttle and braking signal from the Odroid, which then goes to the onboard Motino. As Tristan mentioned, the onboard Motino is also connected wirelessly to an offboard Motino, which serves as the device's kill switch. It allows us to enable and disable driving on the car, as well as force kill it should any safety concerns be brought up. And in terms of braking, the brake motor receives signal from the Motino. It then turns the brakes either on or off. It's detected by a limit switch, and that feedback is read back into the Motino. The throttle is simple. We just send a signal between 0 and 5 volts to engage the steering. So the new system that we're using, or proposing, uses a PG188 gearbox, which means it has a gear reduction of 188 to 1. It is rated for 39 foot-pounds, or 470 inch-pounds of torque. That's much more sizable than what we believed the original gearbox, which turned out to be a speed reducer, was rated to. And then we have plans to get various forces out of that gearbox using 2 different motors. Listed here, we have a Bainbot 775 motor and a Vex 775 Pro motor. They both use the same housings, and they have different outputs. As seen here, the numbers in parentheses are the motor's free speed and stall torques. The numbers not in parentheses are the outputs through the gearbox. So the original Bainbot's motor is able to deliver roughly 400 inch-pounds of torque, which is significantly greater than its predecessor. And should that still not be enough, we can strap a Vex Pro 775, which is able to achieve much more torque. Should we go with the Vex Pro motor, or it be implemented in further designs, we need to have current limiting as well as PWM limits so that the system does not tear itself apart physically. We've also had to upgrade the motor controller used. It is going to be proposed as a 100 amp 12 volt brushed DC motor controller, also made by Vex, so the motors and motor controllers seamlessly will integrate together. I'm going to pass this off to Paul, and he's going to explain some of the results of our testing.
Thank you, Ryan. All right, so we recently just completed our test plan. Going into the design freeze, we were, obviously, our braking system was down. So any tests that had braking in it failed by default upon inspection because there wasn't a braking system. Going to the design freeze as well, throttle was also not operational, as you all saw last time. But we did pass our manual autonomous changeover. The times were much less than expected, so going from autonomous to manual was approximately 9 minutes. We predicted that it would be 20 minutes. It was required to be at least 20 minutes in your SDRD. And then it was 16 minutes to go back from back to autonomous from manual mode. So it's a little bit harder to put it together than to tear it all apart. And then going into the design freeze, because due to safety concerns, we were allowed to make certain changes that we talked through with our advisor that regarded to safety and safe operation of the vehicle, so we could do these tests. One of them was to add on a tethered kill switch, and to upgrade the wiring and to upgrade the connectors. So coincidentally, after we did this, we passed our safety and PRS and APRS rule compliance test. And as far as the partial pass of test 2, we did pass our LiDAR test. It can detect obstacles within 6 meters, as was required in SDRD. However, because we don't have our lateral sonar sensors, we could not pass that part of our test. And then I'm going to pass it back to Ryan to talk about the scope of the project.
So throughout the project, we've had different ambitions and goals with how we would like to complete the project. Throughout the first semester and the early stages, kind of the setup of implementing the design, we were very ambitious. We wanted to have a fully implemented design, one that would solve all the problems possible, conceivable to the car, and allow us to compete at a very high level right out of the gate when this car is put on an autonomous power racing series course. We wanted streamlined communications between all devices and have all of our various subsystems working together beautifully. In reality, most of our systems are functional. However, they are a little rougher on the edges, and we do need more time to refine them. Namely, the braking and throttling systems, as well as a little more time to fully develop the auxiliary vision sensing that Paul touched on previously. And so some of the difficulties that we have faced along the way are a lot of unforeseen challenges. We had a lot of difficulty getting accurate and robust sonar housings. We had a lot of cracked 3D printing and had to do some analysis to figure out why they were failing, where the stress risers were within the parts, as well as what we needed to do to achieve accurate tolerancing. We also did not appropriately gauge our resources. The resources that namely we missed the mark on were time, money, and manufacturing resources. We had a lot of metric that we were using, whether that be bolts, shaft sizes, etc. The manufacturing capabilities that we had access to were set up mostly for standard of the mid to large range meaning sizes of bolt 10 all the way up to quarter, 3/8, etc. We were using a lot of smaller scale, anywhere from 440 up to 1032, and in various places quarter 20. And with regards to time and money, as stated, various systems that we have are in various states of completion. A lot of them are rough around the edges and do need more time to polish off. We didn't anticipate the time being an issue, and clearly that has seemed to be a large issue. And monetarily, we tried to keep things, keep our systems as minimally expensive as possible. The system that suffered the most from that was the braking system. We thought that we could achieve the braking system with a cost of less than $100. In the new proposed design change, it costs over $300. So to recap what we've talked about, we went through our high-level SDRD requirements. We talked about the various systems on the car, ranging from the steering, vision and control system, the steering controllers, as well as the other controllers on the car, the braking system, our test plan results, the current state of the project, and various lessons that we learned along the way. This time we'll open up to questions. Yes.
You had a gearbox that tore apart, right?
Yes.
So at some point, you would have had to done your design, and you would have had to look at different parts, and then you chose that gearbox. So what happened with, you bought one and it got ripped up? What happened with that?
So what happened was initially we took a force measurement at the handle of the car, which we, okay, so the question was, why do we believe that gearbox failed? What design process led to us selecting that gearbox, and how did we assess it once the damage had occurred? So initially we took a force measurement off of the handle, which had the brake line attached to it. We were able to measure the distances from the point that we applied the force to the pivot points of that handle, and also where the brake line met into the handle. From those measurements, we were able to turn the force into a torque required to pull the brakes. And then we used that torque, and we said we want a pulley of this size. I believe its diameter is 0.84 inches. And then from that, we get back to a force, and from the force, we were able to select a gearbox that we thought was adequate. We went through a bunch of different, we had a bunch of different gearboxes that we were considering. A lot of them were eliminated due to monetary concerns, budget concerns, and we ended up going with the Econ 56 RPM gear motor. We at the time believed that it had enough, it had the capabilities to deliver enough force to pull both brake lines. We found out that somewhere along the way we either miscalculated or didn't understand how the forces would change when we went from autonomous to manual steering, and vice versa. And as a result of that, we had a motor that was insufficient. We were trying to make it achieve torque that it just wasn't designed for, and we believe it was more designed for reducing speed than applying greater torque, and it failed. Tore it apart, found sheared gears, teeth missing, and decided that we needed to beef the system up. Yes?
So I think you guys didn't quite have the implementation of the sonar and the LiDAR, but I'm curious, you were able to detect objects. What was your control log from there? So once you saw an object, how do you decide which direction to turn or what you should do?
So as far as autonomous operation goes, what happens, we had a slide that somehow didn't make its way in to explain this more, but what happens is the LiDAR data is taken and it's sent to a program or a node, a control node, that takes that LiDAR data, it's like a vector, and it looks at it to see if any obstacles are too close to the vehicle. If they're too close, it stops the vehicle. So it's kind of an early collision detection system. If it's okay, if everything's all right, it'll take that and it'll feed it into the neural network as an input layer, on the input layer of the neural network. And then the neural network decides from there, based on how it was trained, how to turn the wheels and how to apply a throttle appropriately. So. It's more or less been trained to react a certain way. So when you train a neural network, you collect training data, and then you take that training data, and that training data is both the inputs to the system and the outputs of the system. A neural network is more like a black box, so you don't really necessarily know what's on the inside. You just know what the inputs have to be to get a certain output. So when you train it, you're taking like the LiDAR data. We're recording LiDAR data, but also like I'm controlling the car too while we're recording with like a keyboard or something, and we're driving around the course. And it's recording also how I'm responding to the environment. And when you train a neural network, you essentially take those stimuli, so the LiDAR data and the responses, and you train the neural network to act the same way. So that's the idea, is that when we take that LiDAR data now, when it's running in autonomous mode, it should respond a similar way as I responded to, because I trained it to respond that way. So I don't know if that answers your question. Okay.
Are there any further questions? All right, thank you very much.